Hello, welcome to the video review of physics review sheet number 1. A few things here. I'm going to provide you just with the answer key written, so if you don't want to listen to it, that's fine. Feel free to scrub forward if you're just looking for a certain problem. And excuse me if I make mistakes or I'm not very eloquent in my explanations. I don't have time to make it perfect. And finally, what else was I going to say? Oh yeah, I'm going to use this time to also kind of re-explain some things because it's been a while. Okay, so let's get started. And I'll just start doing this and feel free to move ahead. So express decimal numbers in scientific notation or vice versa. I could ask something like this. So let's go ahead and give it a try. I'll try to hurry. Now, one technique people use is just they move a decimal place one way or the other and figure out what the scientific notation is based on that. So for numbers bigger than 1, we take the decimal, which I just drew there, and we need to move it over 1, 2, 3, 4, 5, 6, 7, 8, because you always want a number in front of the decimal between 1 and 9, right? So I moved over 8, so that's going to be 4.493 times 10 to the 8th. Okay, so far so good. All right, let's go to number or letter B. For that one, we need to go in the opposite direction. So we're going to go to the right. Let's see how many. 1, 2, 3, 4. Because you want the decimal to be, after the first number. So that's going to be 2.041 times 10 to the negative 4th. We had to move it over 4. Now, another way that I can think about this for the numbers that are less than 1, decimals, I kind of think if you look at this, 0.000, there are 3 zeros before we get to the 2. I always remember to add one more, and that's what the negative exponent is. So if that has 3 zeros between the decimal and the first number, I think 10 to the negative 4. Okay, but it's up to you. Let's do C, 1.56 times 10 to the negative 5th. So one way to do this is to say actually I'll need a little more space. Sorry. I'll do 1.56. But I need to move the decimal point over 5 places. So I'll go 1, 2, 3, 4, 5. And that's where I put my decimal, but I fill it in with zeros. And I can put a leading 0, which I prefer. 0.0000156, that's the answer. But again, notice that if it's negative 5, that tells me I put 4 zeros between the decimal and the 1. Again, don't do that if you're not used to it, so you'll get confused. Okay, what about 499 times 10 to the second? You probably already know it's 499. But if you do it this way, you go 4.99, and now we're going to move the decimal place over twice, so we get 499. All right, let's move on. Number 2, I'm not going to ask you a question on the test about this, but I remember, and I always remember, that people have trouble when they, with their calculator, when they have numbers, multiple things on the bottom. So just to try it out, what you do on your calculator is you type in 3, and then remember your second EE buttons. What you would do is you'd press 3, then the second button, then EE button, and then write just -8. Don't put 10. If you want to write in 3 times 10 to the negative 8th, just use parentheses like crazy. Okay, but back to the problem. You put in your 3 second EE -8, then you say divide by, and then on your calculator, open a parentheses. And then type in that number, which I prefer you to write it as 8 second EE 7, and then multiply it by 25, and then close your parentheses on your calculator. So do that on your calculator, and you won't get weird answers. And when you do that, you end up, if you did it right, 1.5 times 10 to the negative 17th. Okay. So let's do a little mini lesson. Again, if you don't care about this, move ahead, about random systematic and errors and mistakes. First of all, mistakes. Those are things that you do wrong. It's not the experiment's fault. It's just that you weren't being careful, you didn't follow directions, you're plugging wrong things in your calculator, whatever. So you drop a beaker and spill things. Don't call that an experimental error. The lab didn't tell you to do that. So random and systematic errors are experimental errors. And one main difference, I'll get to another difference when we do the problem, is that a random error is some kind of error that will sometimes make people miss let's say the small side. They get too small of a number compared to what they should be getting. But sometimes it'll make you get a number that's too big compared to what you should get. So randomly, it could cause you to get something too small or something too big. In other words, about half the people, if like you have a classroom of 16 students, around half of them will get too small of a value, and about half will get too large of a value. A systematic error is an error that causes everybody to miss to the same direction. So either it's causing everybody to get a value that's too big, or it's causing, some other kind of error is causing some people to get, or everybody to get a value that's too small. Systematic does not mean everybody misses it by the exact same amount. It just means the direction that you miss it. Okay, so let's go ahead and try these. The actual length of an object is 8.9 inches due to an error. This is what we got: 9.2, 9.4, 9.1, 10, 10.6. Notice they're all too big. So to me, that sounds like a systematic error. The actual length is 8.9 inches due to an error. We got 8.2, 9.3, 9.1, 8.7. Notice how we're missing it to both sides. So that is a random error. It causes people to miss on either side of the actual value. We averaged our data, which helped minimize the effect of the error. That's the thing I mentioned a little bit earlier that I'd get to. Because random errors cause about half the people to get a value that's too small and about half to get a value that's too big, if you pooled the data and shared your data and averaged it, it tends to cancel out each other. So it helps to lower the overall error. So this tells me this is a random error. Because systematic errors cause everybody to miss the same direction, if you averaged the values that you get with the systematic error, it's still going to be too big, right? All right, dough. We forgot to measure the volume from the bottom of the meniscus. So all our volumes are too high. That is a mistake. You should know not to measure from some other place. You always, as we'll see in the next problem, measure from the bottom of the meniscus. So you made a mistake. Don't blame the experiment for that. We wanted to find the speed of a ball dropped from 3 meters if there were no air, but air resistance slowed it down. So is that going to cause some people to get too fast of a speed because of the air resistance and some people to get too slow? No, everybody's going to get too slow of a speed because of this air resistance. So because everybody's missing it in the same direction, that is a systematic error. Okay, number 4. So I'll probably ask something about, or a couple problems about how to measure something. Whenever you're using a device that has markings on it, you always report as your last digit one more digit to the right than the smallest markings on that device. One more digit. Okay, so let's just go ahead and do these and you'll see what I mean. And hopefully this will be easy for you on the final. So looking at this graduated cylinder, we always measure again from the bottom of the meniscus, like right there. Okay. Now what helps sometimes is to write the numbers for each marking. What is that right there? Well, this is 35, right? So this is 36. And what's that? That's 37. What are the smallest markings on this device? The 1 milliliter or 1 cubic centimeter place. That's the same thing. A milliliter is defined as a cubic centimeter. So if it's marked to the ones place, we need to go one more digit to the tens place. So we're going to say it's 36 point something, right? Well, how far in between? I'd say about halfway between. So I'll say 36.5 milliliters or cubic centimeters. So again, we're going one more digit than the smallest markings. I'll probably say about 5 more times over the next problems. In other words, you're making a guess between the smallest lines. All right, let's do the next one. So you should remember how to do a triple beam balance. You add up the 3 beams together. So notice it's 520, and it looks like 1 point something, but we're going to zoom in and look at that. So let's zoom in, which is this thing over here to the right. This is 1.1 right there, right? And this is 1.2, I think, right? So what is the smallest marking? So these are all grams. Isn't the smallest markings on this whole thing to the tenths of a gram? Sorry about that. Because each marking, those 2 markings that we're looking at are 1.1, 1.2. So if the smallest markings are to the tenth of a gram, what digit are we going to go? To the 100th. So to me, it doesn't look like the tip of that little point is quite at the 1.2. So what would we say it's at? Well, I think it's at about, kind of going down here, about 1.19. Notice I'm going one more digit than the smallest markings. I'm going to the hundreds place. So adding all three of those together here, I do 500 plus 20 plus 1.9, 521.19 grams. And pretty much all these with the triple beam balance are always going to be to the hundreds place, so you can kind of anticipate that. Okay, let's get to the bottom one, and that's using a ruler. Let me zoom back out. So let's do the blue line. We're starting at the 0, and again, what might help you out is to realize what these markings are. This blue one right here is, or not blue one, that black one, is about 4.3, right? And this one is about 4.4. So we're in between 4.3 and 4.4. We're making a guess between those two. Let me zoom in a little bit more. That looks like it's not quite on the line. It's about right here is right there. I'm gonna go ahead and say that's maybe at the 1. So notice I need to go one more digit. It's marked to the tenths place, 4.3, but I need to go one digit farther, so 4.31 centimeters, because that's in centimeters. Now this red one, pay attention, we're not starting at 0, we're starting at 5. And so this mark right there looks like it's the 6.8 mark, right? So be careful, it's not 6.8 long, it goes from 5 to 6.8. Now, be careful, we say 6.8, but do I stop at 6.8 and say centimeters? Nope, because it's marked to the tenths place, so we go one more digit. So to me, it looks like it's right on it. So I'm gonna go ahead and say 6.80 centimeters. Okay, again, one more digit than the smallest markings on your device. All right, let's try this red one over here. We're starting at the origin. Oh, sorry, I missed that one. See, I told you I'd make a mistake, but I'm not gonna re-record it. I did exactly what I said not to do. We're starting at the 5, so 1.80 centimeters. The red one here starts at the origin, and notice it's ending right at the 4. So should I say 4 centimeters? No. The smallest marking is the 1's place, so we're going to say 4.0 centimeters. And the idea is, a reader, if you wrote down 4, they would think, oh, I guess they're guessing the 4, so maybe it's 3, maybe it's 5. They're not sure about the tenths place. Here we're saying, we're really sure about the 4, we're just not quite sure. We're making a guess to the tenths place. So we write 4.0. Now this blue one, yeah, it's about right there. That's about a third of the way to the 1 maybe. So I'm going to go ahead and say 0.3 centimeters. And again, notice I'm going to the tenths place because the smallest markings are the 1's place. All right, we'll keep going. So conversions. Yes, I will provide for you the imperial conversions like are written there, whichever ones you need. But you have to write down on your note sheet, please remember to do this, all the Greek prefixes, not Greek, what am I saying? Well, I guess they're Greek, I think they are, but the metric prefixes, what I meant to say. And I think, if I remember off the top of my head, the ones you need to know, for the ones bigger than 1, kilo for 1,000, mega for 1,000,000, giga for 1,000,000,000, and tera for 1,000,000,000,000. And then the ones less than 1, centi for 1/100th, milli for 1/1000th, micro for 1/1,000,000th, and nano for 1/1,000,000,000th. Okay, so write those down. So let's try some. Now these I meant to just kind of do in your head, just to get the logic of it. So 1 microsecond, I'm gonna show you like a mistake and you'll tell me what I'm saying here. Think about your answer to see if it makes sense. How many seconds is 1 microsecond? So let's say you knew micro had to do something with 1,000,000 or 1,000,000th or whatever, and you said a microsecond is 10 to the 6th seconds, 1,000,000 seconds. Now, does that make sense? I think you all know that a microsecond is really small, faster than a blink of an eye. How can you say 1 microsecond, that really short time, is equal to 1,000,000 seconds? Does not make sense. So what we need to do is to say, no, it's not 1,000,000, it's 1/1,000,000th. Okay, that makes better sense. Okay, what about 1 teraliter? That's a big volume, equals how many liters? Again, I'll purposely do it the wrong way. I'll say, I know tera is something like a trillion or a trillionth. So I'm gonna say, a teraliter is a trillionth of a liter. Now think of that. A trillionth of a liter, you couldn't even see that. And a teraliter, I think you have an idea, is a huge volume. So that seems wrong. So let's get rid of that and say that it's a trillion liters in a teraliter. That makes more sense. A liter versus a megaliter. Again, doing it the wrong way, you'll say, oh, there are 1 million megaliters in a liter. Really? A liter is like, a little bottle of water. 1 million megaliters? Can't be right. So let's change that to there is 1/millionth of a megaliter in a liter. Make sure you know capital M is mega, not milli. And then a gram, again, doing it wrong, you might say 1 gram equals 10 to the, because it's like a billion or billionth, -9 nanogram. Well, a nanogram is already incredibly small mass. So now you're saying it's a billionth of a nanogram, and a gram is like a paperclip? So that can't be wrong. That can't be right. So there are 1 billion nanograms in a gram. So that's what I meant by think about it logically, but of course you can write down all these relationships that you want. So let's do some conversion factors to solve some conversion problems. Let's convert 340 meters to micrometers. So what is the relationship between a meter and micrometer? I'll do it 2 ways just so you get the idea. Well, if I say I have 1 meter, how many micrometers is that? Well, a meter is pretty big and a micrometer is pretty small. So it's probably that there are 1 million micrometers in a meter. So let's use this, and I'm going to try it a different way. So how you do conversion factor is you use your parentheses, and again, you don't have to show your work, but it might help you get the right answer. Just don't spend too long doing this. I'm not going to ask a lot of conversion. There are probably like 4 conversion problems on the final. Don't sue me if there are 5, but something like that. So notice we're currently in meters. And so if it helps you, draw it like that. It reminds you that the meter is in the numerator. So we need to put one of these on the bottom and one on the top. We're trying to cancel the meters, right? So I'm going to put 1 meter on the bottom so the meters cancel, and put the million micrometers on the top. And so on your calculator, what you're going to do is you're going to take 340 and multiply by 10 to the 6. And what you get is 3.4 times 10 to the 8th micrometers. Okay. Now let me do this slightly different way, because maybe you didn't do that same conversion factors. Let me erase some of this. I'll erase this. Well, won't need to later, but just erase this. Sorry. Haven't used my Notability in a while, so forgot how to do all the buttons. Anyways, so let's go to conversion factor. But let's say that you use, instead of this, you said 1 micrometer, correctly you said, is equal to 10 to the -6 meters. That is true, okay? But now what you would do is, we still are in meters, so we're gonna put 10 to the -6 meters on the bottom, so again, the meters cancel, and 1 micrometer on the top. This time you're gonna put in your calculator, let me change the color here for my, blue is a little bit too dark. We'll try orange. We're gonna take 340 and divide by 10 to the -6, and unsurprisingly, you're still gonna get 3.4 times 10 to the 8th micrometers. Okay, so you could use any version, just make sure you're putting the right thing in the numerator and denominator to cancel. Okay, let's go a little quicker on this one. I'll just do it one way. So we're gonna take our 450,000 grams and we're gonna convert it to gigagrams. So again, this is like that over 1. So the relationship, I'll write it maybe over here, be a little sloppy, is that I'll write it this way, 1 gigagram, that's equal to 1 billion grams. Again, I'm not gonna explain that, but hopefully you can get that. So we're gonna put grams on the bottom so that they can cancel, right? And then put my gigagram, sorry about that, on the top. So what you're gonna do on your calculator is put in 450,000 and divide by 10 to the 9th. And then what you get when you do that is 0.00045 gigagrams. And if I get an answer wrong, come talk to me and I'll let you know if I made a mistake somewhere. All right, now this one, yes, I'll probably do 1 or 2 of those little conversions, but I will ask you one like number 9 and probably something like these others. Maybe not even as simple as 9, but let's just do those for practice. These, we're trying to go from one prefix to another. Now, most people don't know a direct conversion between nanometers and megameters. You're pretty smart. You can figure it out. I wouldn't say smart, but you're pretty quick with numbers. I'm going to do it in 2 steps. Now, I'm going to do it a longer way, really quick, not really quickly, kind of longer, but then I'm going to try to make it a little bit quicker. Enough explanation. Let's try it. So 52 nanometers. I'm going to go from nanometers to the base unit of meters. So I'm going to go 2 meters and then meters to megameters. So I won't write it on the side, but there are 1 billion nanometers in a meter. So since I'm trying to cancel nanometers, I'm going to put 1 billion nanometers on the bottom, and that's equal to 1 meter, right? It's not that 1 meter equals 10 to the negative 9th nanometers. So I put the nanometers on the bottom because this is like 1 over 1, right? To cancel the nanometers. So if I do that, I'm going to get, I hope I did this right, 5.2 times 10 to the, what is that? So that's negative 8 meters? Is that right? I hope so. I'll find out at the end because I know what the answer is supposed to be. Because it would be 5.2 times, yeah, I think that's right. But now I need to get to megameters. So instead of rewriting it, I'm going to say, let's go between meters and megameters. Well, 1 megameter is 1,000,000 meters, right? So I'm going to put 10 to the 6 meters here, and that's equal to 1 megameter. And I put the meters on the bottom so the meters cancel. And so I'm going to divide 5.2 times 10 to the negative 8 by 10 to the negative 6. And when you do that, you get 5.2 times 10 to the negative 14th megameters, right? And that is the right answer. Okay. So you could do that, convert twice. But what saves a little bit of time, let me erase this. Okay, I need to change the setting. It changes back to pen automatically. Didn't mean to do that. Let me erase those. Let's just do the 2 conversion factors consecutively. So notice that first conversion factor got rid of nanometers and left me with meters. But now I need to get rid of meters. So let's go back and say that there are 10 to the 6th meters in 1 megameter. And I put them on the bottom so they cancel. And then when you put it in your calculator, you'll appropriately get 5.2 times 10 to the negative 14th megameters. Okay. Let's do this conversion factor without so much explanation. I'm just going to do it again in 1 step with 2 consecutive conversion factors. So I'm going to go from gigaliters to liters, and then from liters to milliliters. So again, remembering this is like over 1, I always like to think of numbers bigger than 1. So I like to think a gigaliter is equal to 1 billion liters. So I'll put gigaliter on the bottom, and I'll say, did I say million? I meant to say billion if I said a million. Is equal to 1 billion liters. So that'll allow me to cancel the gigaliters, and now I'm in liters. But now we need to go from liters to milliliters. So there are 1,000 milliliters in a liter, but we need to cancel the liters, right? So I put liters on the bottom, and I put that's equal to 1,000 milliliters. So I forgot to say this. Let me go back. Well, I'll go ahead and solve this one. I'll go back and say something about the previous one. Let me get actually a little bit lighter color. We'll do our yellow. Here, we would take on your calculator, and what you would write or type is 0.041 times 10 to the 9th times 1,000. We got to multiply everything together. And when you do that, hopefully I got this right, it's 4.1 times 10 to the 10th milliliters. But let's go back to the previous one. What you do on your calculator is do 52 divided by, now notice there are going to be 2 things we need to divide by. So please pay attention. Do 52, divide by, then open a parentheses on your calculator. And once you say parentheses, type in 10 to the 9th times 10 to the 6th, close your parentheses, and then hit enter, and you should get the right answer. Okay, let's keep going. Let's blitz through these. Not really, I'm going slowly. Now here's some conversions where you'll need to be able to convert from a metric to a imperial or vice versa. So again, I'll give you conversions between, or at least one conversion between metric and imperial to allow it to happen. So we're going to start with 100 meters, and we want to end up with feet. Now, if you look at the given information, I don't give you a conversion between meters and feet, but notice I give you feet to inches. And, well, I'm sorry, not that one. That's not important. There it is. That's the one that everybody memorizes anyways. So what I'm going to do is go from meters to centimeters. And then once I'm in centimeters, I can do the conversion to the imperial units. So let's do that. So remembering that this is like over 1, let's get to centimeters. So of course there are 100 centimeters, not 1,000. In 1 meter, that'll allow me to cancel meters, right? And then now that I have centimeters, I'm going to go to the imperial units by saying that there are 2.54 centimeters per 1 inch. And I put centimeters on the bottom to cancel. And now I need to get the feet. So everybody knows that there are 12 inches in 1 foot. And I put inches on the bottom, so the inches cancel. And look at the only thing I haven't canceled yet is feet. So on your calculator, you're going to type 100 times 100, then that's it, divided by parentheses 2.54 times 12, close parentheses, and then you'll get the answer, which is 328 feet. Now, again, you don't have to show your work. I should mention that. Here in this old review sheet, I said, show your conversion factors. So if you wanted to, you could write down extra conversions and maybe get lucky that I'm going to ask you a conversion between meters and feet, and between meat and feet. And you could write down that 1 meter equals 3.28 feet. But of course, I can do trickier ones that you'll probably never write down, like how many inches per hour squared are there in something else. But anyways, do it any way you need to. Okay, speaking of which, there are some things that you need to convert where you have one of the units squared or cubed. And there are different ways of doing it. I think this year was the first year I did it a different way. So let's go ahead and just start this one. I have 240 inches cubed, and I want to end up with centimeters cubed. Well, I know there are 2.54 centimeters per inch, but if I did that as my conversion factor, like I said, again, this is like over 1. If I said 1 inch and 2.54 centimeters, of course, putting inch on the bottom so it could cancel, is that solitary inch going to cancel inches cubed? No. So what we need to do is we need to say 1 inch cubed, and then that inch cubed will cancel that inch cubed, right? But we also need to cube that. So that will allow us to get from inches cubed to centimeters cubed. So what you need to do is multiply your conversion, not multiply, but raise your conversion factors to the appropriate exponents. So when you do this on your calculator, you would type in 240 times 2.54 cubed. So don't forget the cubed. And then what you're going to get from this is 3,933 cubic centimeters. Okay, so know how to do that for your cubes or squared. And finally on this page, convert things where you might have to convert a denominator. So let's just go ahead and do this. 10 miles per hour. And we want to end up, I'll write it over here, feet per minute. We need 2 things. We need to cancel or go from miles to feet in the numerator and hours to minutes in the denominator. So I always just by habit go with the numerator first. So we all know, even though I'll give it to you, that 1 mile on the bottom, so we cancel, is 5,280 feet. And that will give us the feet that we want. So we're done with the numerator. Now hours, I'll go ahead and just do it the quicker way instead of saying, okay, you must only you must go from hours to, I'm sorry, we are going to minutes. Sorry, I was going to say if we wanted to go to seconds, I said the shortcut would be 3,600 seconds equals an hour, but we're only going to minutes. So notice we need to go use 60 minutes equals 1 hour. But which side does 1 hour go on? On the top this time, because notice hours are on the bottom. So we need to cancel the hours, so we put 1 hour equals 60 minutes. Also, we wanted minutes on the bottom. So on your calculator, again, what you're going to do is go 10, don't forget the 10, times 5,280 divided by 60. And when you do that, what you're going to get is 880 feet per minute. Okay, how you hanging up? Hang on. Okay, let's do one more conversion, a big one here. I won't ask one quite this long just because I don't want you to spend, so much of your time doing conversions, but it's just for practice, we'll do this long one. Okay, let's convert 5 terameters per year squared, that's an acceleration if that looks familiar, to kilometers per hour squared. Okay, let's start. So let's deal with the numerator first. We're going to go from terameters, since we've got to go to kilometers, we're going to go from terameters to meters and back to kilometers. So do it in 2 conversion factors. So 1 terameter equals 1 trillion meters. So that'll get rid of the terameters. But now we need to get to kilometers. So there are 1,000 kilometers. I'm sorry, did that wrong? Just as I was starting to type it, I realized I was doing that wrong. Sorry. There are 1,000 meters in a kilometer. So I'm going to put 1,000 meters times here and a kilometer. So that will cancel the meters. And now I have kilometers per year squared. But now let's deal with the year squared. We need to get to hours. So remember, when you have a squared, we're going to do this little trick. 1 year equals 365 days, right? But since it's squared, I need to say 1 year squared so that I can cancel those years squared, right? And that's equal to 365 days squared. But we need to get to hours. So to convert the days to hours, we know that 1 day squared equals 24 hours squared. And that'll cancel the day squared here. And that'll give us our answer. So what you do on your calculator, this is often where people make a mistake, 5 times 10 to the 12th, and that's it for the numerator. Then say divided by, open parentheses, 1,000 times 365 squared. Even though I canceled out that squared, I shouldn't have done that. You need to square the 365 times 24 hours squared. Then go ahead and close your parentheses and hit enter. And what you get is 65, rounding off, 0.2 kilometers per hour squared. Some kind of acceleration there. Right. I probably won't ask you one like 14, but just to remind you, the percent error is how far you're off absolutely, your absolute error, how much you missed the target by, divided by what you should have got, your accepted value. So I'm going to do it kind of the official way, that the percent error is the value you get, 3.09, minus the accepted value, 3.14. And you divide by the accepted value. So the top is actually your absolute error, which is negative 0.05, but we're dividing by that, and you multiply, I forgot to say that over there, but to convert it to a percentage, you multiply by 100. And you'll end up getting negative 1.59%. Now, actually, I don't care, and most people don't care whether it's positive or negative. By convention, a positive percent error means your value was too big, and your negative error means your value was too small. But typically, people just take the absolute value and just say 1.59%. Now, again, I doubt if I'm going to ask that, but be ready for it. So if you want to write down that formula for percent error, you might as well go ahead just in case I do ask you. And honestly, I'm not trying to be tricky here. I just can't remember if I do ask it or not. All right, so a quick little lesson for 15, won't take long, is going back to this, and there'll probably be a question or two about this type of problem like in number 15 and 16 here, is that a linear relationship between two variables is that should have been, anyways, so for y and x or between two other properties, is that if it forms a line as opposed to a curve, then it is a linear relationship. Now, I'll get to proportional in a second, but for now, just know that a linear fit is when you have a line. So which of these does not show a linear fit? Well, only E. That's the one that is not a line. Pretty simple, right? A proportional relation, you have a linear relationship, and the linear relationship has an y-intercept of 0. In other words, it intersects the origin. Now, one thing that I made a mistake here is I didn't specify that where the x and y axes meet is actually 0, 0, but I guess you could have assumed that. So again, a proportional relationship between two properties is a linear fit that specifically has a y-intercept of 0. In other words, it intersects the origin. So which show a proportional relationship? Well, that's going to be A and C. B isn't, because it's linear, but it's not intersecting the origin. Same thing for D and especially for F. Now, here's what's important about a proportional relationship is if two things are proportional to each other, if you double one of them, the other doubles. If you triple one of them, the other triples. If one of them is 5.8 times bigger, the other one is 5.8 times bigger. That is not true of just a normal linear relationship. So a proportional relationship has that value. So it says, look at graph B. If X doubles, does Y double? Well, is that a proportional relationship? No. So the answer is no. Okay. But for A and C, if X doubled, Y would double. Okay, so let's try this one. By convention, we always put what we call the independent variable on the x-axis and the dependent variable on the y. You should know that. The independent variable is the one that, usually it's the one you have control over, the one that you're changing. And the dependent variable is the property that changes as a result of your manipulation. So for example, if we're changing the volume of a substance, of course, its mass is going to be different as a result. So what's the dependent variable? The mass. And if you think you're going to forget, write it down in your notes. Now, what's the density of the material? Now, I meant for this problem, because we did something like this for a lab, is we found out that the slope of a line for mass times mass versus volume, the slope gives you the density when you are graphing mass versus volume. So one way to solve that question, what is the density, is to find the slope. And remember, the slope is the rise over the run. And I'll show you another way of doing this too, is let's just use the whole line. The rise is 20 grams, and the run is going to be 5 cubic centimeters. So the rise over the run, the slope, is 20 grams over 5 cubic centimeters, or 4 grams per cubic centimeter. I think this might be on the final, so pay attention. But also, we learned in that lab, if you didn't already know it, that density equals mass over volume. You might want to write that down in your notes. Hint, hint. Well, actually, I shouldn't say hint, hint, because I actually don't know if it's in the final, but you might as well write it down just in case. Again, I'm not trying to be coy, I just really don't remember. So anyways, we could have just solved it with that by just taking that point and saying, hey, look, I have a 20 cubic centimeter plate, a 20 gram piece, that's my numerator, and my volume is 5 cubic centimeters, and just divide and get that. Now, the equation for the line, of course, is y equals mx plus b. I don't need to explain that to you. But let's go ahead and write it in terms of what y and x and m are. So y represents the mass. The slope is, I'll go ahead and put the unit in, 4 grams per cubic centimeter. X represents the volume. And what's the y-intercept? 0. So we could just leave it like that. Now, here's a follow-up question. What would be the mass of a 12 cubic centimeter piece of this material? Well, that's the volume, right? So all we need to do is plug that in there, or kind of use this, now that we know D is 4 grams per cubic centimeter, and plug in 12 for that and solve for mass. So just plugging in 12 there, I would say, just go ahead and think of that as being 12 there. You would get that the mass is 48 grams. Okay, I'm kind of going fast just to not waste your time too much if you know these things. All right, let's do 18 first, because I want to bring up actually the difference between a scalar and vector. I could ask a quick multiple choice question about that. A scalar is a property that has no direction as part of its definition. So like, what is your mass? Your mass is 50 kilograms. There's no direction. What time is it? It's, how long has it been? It's been 2 minutes. There's no direction there. A vector is a property that has a direction, like a spatial direction associated with it. And the other difference is that for vectors, we're going to put an arrow over the symbol. So I won't write that down. You just kind of heard me. So let's just practice this, because it's important to know the symbols, as we'll see a little bit later, for each of these. So time is t, the symbol, not the units. Position we'll use as x, but that's a vector, so we put an arrow over it. Velocity is v, it's a vector. Now the units, the SI units, for both imperial and SI, it's seconds. For position, it's going to be meters, but for imperial, it's going to be feet. And then velocity is just a combination of those. Meters per second for SI, and feet per second for imperial. Okay, know those. Circle the vectors. Position, yep. Distance, nope. Time, nope. Velocity, yep. Speed, nope. All right, so let's do a little mini lesson here before we kind of do number 20. This might take a little bit, but it might be good for you. Notice that we're doing position graphs here. So when I did this test and this review, I didn't want to confuse you too much, so I didn't include velocity graphs on the first test. I'm going to just be kind of weird here. I'm going to call this west and this east here. And so, of course, for the final, there could be position and, well, not could be, there will be position and velocity graphs. So pay careful attention whether we're talking about position graphs or velocity graphs. So let me just kind of review, trying to do this quickly, so I can get different colors here. So this green one, if you have this, is your position changing over time? Let's say that this is 3 meters. No, I'm staying at the same position relative to the origin as time passes. So this is stopped. If you don't think you'll remember that, put it in your notes. That for a position graph, a horizontal line means your velocity is 0. You're not moving. What about this? Well, is your position changing over time? Yes. So a line also means it's a constant velocity. Which direction are we heading there? We're heading to the west at a constant velocity, right? Because we're heading farther to the west. What about if I drew a line like this? We're still heading to the west, but which one is faster? The steeper one. So the steepness, if I can say that, is tells you how fast it's going. Now, what about some other weird directions? What if we'll do magenta here, that I'm going this way? Which direction am I heading? I'm in the west, but which way am I heading? I'm going to the east. I haven't got there yet. I haven't passed the origin, but I'm heading towards the east. Similarly, this is heading towards which direction? The west. I'm not in the west yet, but I will be soon. Now let's do a couple of I'll do this first. What if I do that one here and it turns around like this? Well, I gave it away, sorry, but I turned the line around. What's special about that point? You turned around because, this refers to the west for that point. But for this, which way are you heading? To the east. So on a position graph, again, this is all going to change for a velocity graph. When it changes direction, you're actually changing direction. And then finally, we'll do this. What does this mean when it curves? Well, notice that it's getting steeper. So it's not a constant velocity. It's getting steeper, which means you're getting faster. Well, what about this? Well, notice that your steepness is getting less, if that's such a term. So this means you're going slower. Okay, that's our review. It was tough at first, but I think you guys got the answers. A car starting at the origin, well, we already know the answer, right? Because there's only one, but finishing it, is going east at a constant velocity. And sure enough, if you look at F, that is a car starting at the origin, heading towards the east at constant velocity. A car starting in the west, now we have 3 choices for that. It starts in the west, but is heading east. Well, yeah, all 3 of them are, but at constant velocity. Well, 2 of them change velocity. Well, I know all 3 of them start at constant velocity, so I could have written this question better, but only one of them stays at a constant velocity, and that's actually the blue one, B. Okay. A car starting in the east, so we only have 3 choices for that. That is heading west. Well, which one's heading west? Well, D and G are heading west, but let's see what it says. Slowing down, so it must be getting less steep. And I don't know if I have it here. I don't care. I'm just going to save a little time. Let's call that purple. So that's going to be the D there. That's the one that's slowing down because it's getting less steep. A car in the east heading west, but speeding up. Well, that's the green one, G. I guess I color coordinated the letters. A car that turns around, so just like I talked about, so I'll just use green again. That car was heading towards the east, and then now it's heading west. So that is curve, I just crossed it out, A. A car that suddenly speeds up when it passes the origin. So that is the red one. So notice how it starts out at a constant velocity, then boom, gets steeper. So that is curve C. And finally, a car that is stopped, I don't have that color, let's call it black, that's E, it's not moving. Okay, so practice those, because I'm sure I'm going to give you probably 4 points worth of position graph stuff or more, including things like number 21 here. And then same thing for velocity graphs once we do that review sheet. Okay, let's get to it. Position graph. So again, pay attention whether it's position or it's velocity graph. Let me get my red color here. At what time does the object cross the origin? Well, that's pretty easy. 10 seconds. That's right here. Remember, this is a position graph. Velocity graphs will have kind of different meanings. At what time or times is the object going in the negative direction? So negative direction is when you're heading kind of, oops, wrong button, heading kind of that way, right? So only one time is that happening, and that's between 6 and 9 seconds. At what time is the object stopped? Well, that's only there, 3 to 6 seconds. Again, I'm kind of going fast, but come see me if you don't get this. At what time does the object suddenly turn around? Just right there. It was heading towards the negative direction, and then suddenly now it's heading towards the positive direction. So at 9 seconds, it suddenly turned around. Okay. When is it going faster? At 1 second or at 7 seconds? Well, look at 1 second right here. The speed is what the slope is at that point. There's the slope at 1 second. Here's 7 seconds right there. What's the slope there? Well, qualitatively, that's steeper, right? It's not much, but it's steeper. So the steeper the slope, the faster it's going. Now here's kind of one that I'm not going to ask, but what's the total distance? That's kind of altogether, what's the total distance you moved? It's not the displacement, it's the total distance you moved. Just get rid of this stuff here. Oops, trying to erase it, didn't erase. It keeps, sorry. I haven't used Notability in a while, and I have to change the setting where it's always kind of resetting the pen. Sorry, you don't care about that. So notice we start at -4 and we end at -2. So we've moved 2 meters so far. But then from here to here, we've moved 4 more meters. Then from there to there, we've moved another 12. So altogether, we've moved 18 meters. Not so important for things. Now, what's the displacement, the delta x? We're just now introducing that, or the change in position. That's just your final position compared to your initial position. So notice we started at -4 and we ended at +6. So what did we change by? We changed by a +10 meters. We went from -4 to +6. Make sense? Now, why that's important is because V average is your displacement, your change in position over time. It's not the distance, the total distance you traveled. We're not going to use 18 meters. We use your displacement. So it's going to be 10 meters, positive, it's implied, over 11 seconds. So that ends up being 0.91 meters per second. Okay. Now I'm going to do a bonus question. I kind of made a mistake. I meant to ask this, but I didn't. Let's say, and be ready to do this. I'm going to erase some things here. What if I wanted to know the velocity at 7 seconds? So in other words, the velocity right there. Well, this is a position graph. You don't read the velocity by seeing what that value is. Here's very important, listen to me. The velocity of a position graph is the slope. Now notice I'm not just using exactly that point. The slope is the same the entire time. So where 7 seconds intersects the line, I have a constant slope. So if I find the slope of that, that is the velocity. So my rise, or in this case a fall, is -4 meters, right? And my run is, 3 seconds. So the velocity, again, is going to be your slope of a position graph, which is your rise, -4 meters, over your run, 3 seconds. So it's -1.33 meters per second. So that wasn't on here, but make sure you know how to do that. Please, please, please. I'm not positive it's going to be on there, but it's something that we like to ask. Okay, let's do a couple of quick questions. We're getting close to the end. Running out of voice here. A TV race car announcer says, the car rounded the curve at a constant velocity of 200 kilometers per hour. What is wrong with that? It can't be constant velocity. I don't know why I crossed it out. Velocity has a direction. It's a vector. If the guy in the car is turning, he is changing direction. Even if he stays at a constant speed of 200 kilometers per hour, because he's changing direction, that means his velocity is changing. So he cannot be going at constant velocity. In fact, his velocity is changing the entire time while he's turning. Okay, I won't write it down. You heard what I said. You run a 50-kilometer race. After 5 hours, you collapse at the finish line, which happens to be also the start line. So in other words, you ended back where you started. What is your average velocity? This was that trick question that people just couldn't accept. Sure, you have a speed that you went. I want to give you credit for that. But your average velocity is defined as your displacement, your change in position over the time it took. What was your displacement? 0. So even though it took you 5 hours, since your displacement was 0, your average velocity is 0. Don't get tricked by that, okay? Now let's do some, again, we're just starting at the first units of dealing with numbers. So let's do these problems first kind of logically, but then we'll do them with that little formula, which is overkill, but we'll just practice it if we want to. So let's find our displacement, our change in position, our delta x. So we're starting at negative 14. You can even draw a number line. I might not even ask one this simple, but there's 0. We're starting at negative 14, and we're ending at negative 22. So we went from there to there. What is your displacement? How far did you go and in which direction? Didn't we go negative 8 feet to the, or just to the negative direction? Yeah. So it's negative 8 feet. We started at negative 14, we ended at negative 22. Now, if you wanted to do that equation, you can say your displacement is your initial, which is negative 14 feet, minus your final, which is negative 22. So when you minus a negative, of course, that becomes, did I do that wrong? I'm sorry, yeah, I did, sorry. I told you I'd make a mistake, so I'm not gonna re-record it. I wasn't not paying attention to the initial and the final. So our final is negative 22. I know that was wrong. Minus your initial, which is negative 14 feet. So negative 22 minus a negative is positive. So yes, you end up with negative 8 feet. So let's do one with north and south. First, let's do it logically. Imagine an origin, and we're starting 315 meters north of that origin, and we end up 260 meters south. Now think about in your head that journey. You would need to go 315 meters to the south to get back to the origin, right? But then we need to go an additional 260 meters to the south to end up there. So we're gonna need to go a total of 575 meters to the south, right? If you can visualize that. But here's another way of doing this. Let's, for the sake of arguments, call, I don't know, we'll call south, I think that's right. I could. Yeah, we'll call south positive. Why not? I'll do that. So this would become positive 260 if we call south is positive. And this will become negative 315. And again, overkill, but if you want to use that equation, you can say your displacement is your final, which is positive 260 meters, minus negative 315 meters. And so that ends up being positive 575 meters, which, because we defined it that way, means it's to the south. Okay, not too hard, but I might ask a quick question like this, but probably not. This is so basic. Find the final position, which we can do in our head or using this equation right there. Your final position is just the initial plus how much you change by. So again, just using positive and negatives, you can do this logically in your head. We start at negative 31, and we change in the positive direction by 12. Doesn't that make it sound like you end up at negative 19? Yeah, it does. Now again, overkill, but your final position is just your initial plus, not minus, whatever you change by. And I think on the sheet I gave you, it's going to have that. So we change by 12. So we, of course, we end up with negative 19. So let's try this one. I'm just going to quickly try to change it. I want you to get used to this when you become a junior and do physics. It's just better to use positive and negatives. I like when we first learn things to kind of make it more concrete by doing east and west, north, south, up and down. So let's go ahead and call, I don't know, I'm going to call it east positive. So this is going to become positive, and then this is going to be negative, right? So we can do this in our head, or let's go back to the original one. We could do it west and east. Is we can say we started 240 west and we changed by 395 to the east. So we're going to end up 155 to the east, right? But let's go ahead and do it this way. So I can say my final position is my initial, which I said was negative 240 meters. Again, doing it with positive and negatives instead of east and west. And I'm going to change, so I'm going to add to this positive 395 meters, or miles, I guess this is. So that's going to end up being 155 miles. And because I said east is positive, then that is to the east. Okay, let's try to finish this up. Now, yes, you are not doing DESPA on this final. It's multiple choice. But I might just kind of do slight DESPA here just to kind of help you solve problems. Of course, these are kind of easy because we this first test, we just had one equation. But now that we have a bunch of equations, you need to be able to find the right equation. So here, I was just giving you that equation, but early on, I just wanted to make sure you can solve for the other variables. So just to solve for the other variables, we already used this. If you divide both sides by t, you get v average equals delta x over t. If you want to solve for t, you divide both sides by v average, and you get delta x over v average. So of course, if you can't be sure to solve those, write them down on your note sheet, okay? So here's the, success in physics often comes down to recognizing what's given to you, recognizing what you're solving for, and then finding the right equation. So that, not that we're going to do DESPA, but that D is actually really important. You want to know what your data is. Now, we were kind of writing it out. If you look at the written answer key, I'm going to write like this equals that equals that. Let's just kind of do it more quickly like you'll do for the final. But you do need to recognize which each of these things represents. So we start at 35 kilometers to the north. What is that describing? That's describing your position, right? And specifically, your initial position. So that represents x naught, or x0, whatever you want to call it. And travels, here's a line break here, 60 kilometers per hour to the south. What is that describing? Well, yeah, your v average. We'll assume it's the average velocity. And we end up 120 kilometers south. Well, that's another position, right? But that's your final position. And also do this. How long does it take? That's asking for t. So that's what you do. That's why it's important to know the symbols for these things. Because once we know these symbols, all we do is look for an equation that has these things in it. So maybe just to summarize down here, we know x initial, x final, v average, and we're looking for t. Now, you would look for an equation. Now, what I like to do is, because I want you to be able to have this skill over here, where you're just being able to easily find the change in position, the displacement, typically this year, I hadn't been giving you like a different equation. So I'm just going to use a different equation here. Now, you might be stuck and say, I don't know an equation. But whenever I give you x initial and x final, what can you solve for? Delta x, the displacement, the change in position. So now that might look familiar. I have delta x, I have v average, and I'm looking for t. What is that? Well, that's t equals delta x over v average, which of course I just quickly solved it from here. That's the original equation here, but I just went ahead and wrote that equation. So what is the change in position? Well, let's kind of do it in our head. Maybe just use south and north. I'll try a different method. We started 35 kilometers north and ended 110 kilometers south. So which direction did we move? We moved to the south, right? By how far? Doesn't that look like it's 145 kilometers? I think so. So 145 kilometers south. And again, you don't have to show your work, but you might just want to jot it down for the final just so you can see what you're doing and not try to do it all in your head. And then the v average was 60 kilometers per hour to the south. So of course, the directions have to cancel. And then the kilometers cancel. So be careful, because I could try to trick you, for those who are listening here, and give you the speed in meters per hour or something, but the displacement in kilometers. You got to make sure your units cancel. Now this is left 1 over hours on the bottom when we cancel, but it'll flip up on top and we'll get the answer. So when you plug that in, you get 2.42 hours. Okay, looks good. What you could have done, I'm not going to go through all this, but I'm just going to point something out here, is I'm going to do something maybe not convenient, but something that you want to be careful here. Let's say that I wanted to get rid of north and south and just do positives and negatives. And here's something I'm going to do. I'm going to call, purposely here, south is, I'll say north is positive. So this 35 kilometers, I'll go ahead and write this down. I'll just do it here. This is positive 35 kilometers, right? Because we're saying north is positive. Well, what is this, the final position? It's going to be negative 110 kilometers south, right? But here's where you need to be careful. Notice the velocity was to the south. So what is the velocity now that I'm declaring north as positive? That would need to be negative. Okay, actually, I won't resolve the problem. I just wanted to point that out, that if you're going to define north and south or east and west being positive or negative, don't forget about all your quantities. So if there's any vector quantity there, make sure you're getting it appropriately north or positive or negative, depending on which direction it is. So again, you don't have to do DESPA, but not that you don't have to, I don't want you to, but all you do, the key thing is understand what's given to you and know what the symbols are for those and what you're looking for in the symbol. And then once you know those, on your given list of equations, find the equation, but just be careful with units matching and stuff like that. Okay, last question. You start, I think it's just not that interesting because we only had one equation for this test. So that looks like initial position. We got an average velocity. I just even told you that, so that's V average. And then this is a time. And it wants to know your final position, X final. Ooh, this might be a little trickier. So anyways, maybe writing it down, I'll just go ahead and do this really quickly. Initial position is 20 miles west. We got T equals 30 minutes. And then the average velocity equals 70 miles per hour. See something wrong here? And this is to the east. You see two different time units? Yeah. So what I'm going to do actually is right away say this is 0.5 hours, because we're going to have to deal with the fact that we have hours here. I could have converted miles per hour to miles per minute, but I think most of you will agree, maybe, that it's just a little quicker to conveniently convert 30 minutes to 0.5 hours. So I know we don't have an equation, even though I'll quickly tell you at the end of this, I wrote down on your equations an alternate one that relates exactly those things with what we're looking for, xf equals whatever. But again, if we're looking for final position, we're probably going to get it from the change in position, because remember, we have this relationship that we know that the final position is just your initial plus the change. So let's go ahead and use our delta x equals V average t. We're almost done here. And solve for what we want to solve for. So our V average, I'll just use east and west, that's fine. 70 miles per hour east. The time is 0.5 hours, so that our hours cancel. And so our delta x is 35 miles to the east. So not that you have to show your work, but you could probably do this in your head. In fact, let's do it. We started 20 miles west, and we changed by 35 miles to the east. So what's going to be the final position? Yeah, 15 miles to the east. But if you, not that you have to show your work, but if you're confused or whatever, you got this equation to say your final position is always your initial, which was 20 miles west, plus whatever it changes by. So it doesn't really make it any easier, but you still can look at that and go, oh, 20 west plus 35 east, that's going to give me 15 miles east. Okay, makes sense? Now, again, I'm not going to do this, especially for these kind of simpler equations that we're using initially, is you could go back and define west as positive, east as negative, etc. But just be careful that if you're going to do that, pay attention whether your speed is going to be, or velocity is positive or negative, depending on if you call your stuff east or, I'm not sure what I'm saying here, call your direction of east being positive or negative. Okay, so that's it. Thanks for listening. I hope you find this really useful. See you soon.